The next technique we're going to learn is just a different way of basically doing the same thing. We've been working with washers and sometimes discs, but sometimes that's not going to work really well. Here's an example. If I want to take this function, which is sine of x squared, and wrap it around this way, around the y-axis, imagine what this is going to look like when I wrap it around. It's going to look something like that. It's got this depression in here. And if I were to try to make a washer like this, I'd have a lot of problems. For one thing, I'd have to solve this, right? I'd have an inverse sine of y, because if I'm doing a washer, this is my dy, I would be taking my integral with respect to the y-axis. So I would be integrating the inverse sine of something, and then there's a square, and then there's square root, whatever. Anyway, so the inverse sine of something. And I also have this problem where the top, this side and that side are the same function, and it would just be a big mess. There's a big mess. You don't want to deal with this. So there's another method, which is called cylindrical shells, that helps us deal with this sort of thing. It's somewhat a little bit more difficult to picture, because for cylindrical shells, instead of making a washer, we're actually going to fit it into concentric cylinders. So the closest thing I have in my kitchen to concentric cylinders are these measuring cups. But what you can see, of course, it's not a cylinder because it has a top, but imagine it didn't have a top. They fit one inside another, right? So, and as you fit them in, the bigger shape grows, right? So that's essentially what we're going to try to do. And let me use some computer images, which are a little bit better looking than my measuring cups here. Share screen. Well, the first thing we might as well start with this one. We already looked at this page because these pages, they're linked there. They're kind of nice. They have both shells and washers. We did this problem, y equals 1 minus x squared revolved around the y-axis. We did it with washers, or in fact, they were discs. So remember, they kind of look like that. Now, if you do it instead with shells, okay, it looks the same, but let's put the loop on. Then it looks like this. All right, so that's sort of weird. Let me pull up a different one. Okay, I could have sworn I had here. This is going to give some idea of what we're really doing, right? So in this case, what we're doing is we're taking a rectangle, but instead of looping it around this way, which would give us a disc, we're looping it around the other way. So let's see it work. So if we loop it around the other way, we end up with this cylinder, right? So that's actually what they're doing when they're talking about the cylindrical shells. They're looping it around the other way. So just like we could figure out the volume of the disc very easily, because it's just pi r squared times the height of the disc, or the thickness of the disc, which was d thickness, what dx dy, we can also pretty easily figure out the volume of this shell, especially when it's pretty thin. So here, what was the, okay, we can make it thinner, and then we can label the parts. Here, I'm going to label the parts here. So this, we call it a shell, has radius and it has height, but it also has this thickness. So what really is going to be the volume of that shell, especially when the thickness is very small? Let's make it even smaller. Ooh, really thin is what we're thinking, right? Then it's pretty much just the area of that cylinder, right? The surface area. So if I think about the surface area of that, well, we know the surface area of the cylinder here. Like I should have a soup can, right? Because it's a kitchen, but we just took out the recycling, so forget it. Oh, no. But if you think about having a can, or you think about having a label on a can, and we're just looking not at the top and the bottom of the can, but just around, then what you can do is you can cut the can or cut the label off the can and unroll it. When you cut the label off the can and unroll it, you have the area of that. So you've got the height of the can and sort of the radius of that circle. So this is the height, and then the radius is just going to be coming into the picture because we're taking how far am I going around. That's going to be the circumference of the circle. So this is going to be 2 pi r. So what I'm going to be doing is I'm looking at this, and for very small thickness, we call it d thickness, it's essentially the surface area times that thickness, okay? So surface area of my cylinder is 2 pi RH. And then the volume of my thin shell, and we'll call it thin cylindrical shell. That kind of would help if I could do that. Is going to be 2 pi RH times d thickness. Okay, d thickness. You probably can't see that very well on the Zoom there. So let me stop the share here for a minute. Should have done that before. So this is going to be the volume. I'll just put it up here. Taking that can and opening it up is the idea. Hopefully you were able to see it on the screen. Not, we can go over it in one of our sessions. I'm going to show you, go back to the cylinder part, because I want to talk about it a little bit more. Specifically this business, when I keep saying D thickness, what does that mean? If I look at this particular cylinder and I'm going to make it fatter so we can see the thickness a little bit. Okay, really fatter. There we go. Let's make it as fat as you can. Okay, so this is obviously too fat, but in any case, you're going to imagine this. And if I look at it, the height is in one direction. In this particular picture, it's in the Y direction. The radius is in the X direction, and the thickness is always going to be the same direction as the radius, right? Because it's the opposite, it's the perpendicular, the thickness is going to be perpendicular to the height. So really, I'm writing D thickness. I could also write dr, but with the washers, the thickness is perpendicular to the radius rather than in the same direction. So that's why I just write D thickness so I don't have to remember. But we'll talk about that later when we compare the two methods. But I just wanted to make that clear. In this picture, because we're rotating around the y-axis, the height is going to be the y, so y equals f of x. The radius is going to be x, and thickness then would be dx. So we'll get to actually setting it up later. I just wanted to have you have a little idea of a picture there. Actually, maybe we'll just do the next one. We'll just go back to this one. Now maybe it might be easier to see what they're doing when they're doing this. So this is the original curve. They broke it up into these rectangles, and then they're taking all these rectangles around. So when they do this, they're showing you that picture of how those cylindrical shells are sort of concentrically in there, and you see how it fills up the whole volume just the way it filled up the volume when we did it with the discs. So let's go ahead and work this out. We'll work out this particular one. Let me get rid of this. I'm just going to write it down, and then I'll make it the screen bigger. Okay. So this was y equals 1 minus x squared from 0 to 1. So let me stop the screen. And just keep in your mind, or you can pull it up because you guys have that link. This was the picture. Whoops, 1, 0, and 1, right? And now we're doing the cylindrical shells. So yeah, maybe it would be better just to pull up the link. So if I wrap this around here, and I draw one of these general cylinders, right? It looks like this. This is the height. This is the radius. And my thickness is in the same direction as the radius. So my volume is going to be 2 pi, and remember it's 2 pi because it's from the cylinder, 0 to 1. Radius is going to be x. Height is going to be y, but that's going to be 1 minus x squared. And d thickness is going to be the same direction as the radius, so it's going to be dx. So this is what my integral looks like. My variable is x, these guys are an x. So I go ahead and just do this integral. It should come out to be exactly the same as the other method. So in this particular, what am I doing? All right. In this particular situation, you could choose to use the discs or the shells, and it's just a personal preference. It's not going to make a big difference. So what do I have? 1/2 minus 1/4, so I have 1/4 2 pi, so 2 pi over 4, so pi over 2 is my answer. Right. I think we did this exact same one, but the other way. So it's not going to make a big difference in this particular problem because we started out with like an easy one so that you could get the picture in your head. Now, I know this video probably going to get a little long, so I'm not going to go through and do the other problem, but I did want to show you, at least from the second site, here, remember we also looked at this one. So we can also revolve around, of course, the x-axis and do shells that way. If you remember this one, the discs looked like this. So the shells, though, are now going to look, well, they look the same, but they're going to be like this. So let's put on the loop and you can see that it's not the same, right? They're going to be these cylinders. Okay. And in fact, you can see you can go to this one and see where they did it. So I don't have to do it. But that gives you some idea, at least, of what those are. And so in my next video, I'll start by doing the one I started out with the sine of x squared, which is an example of one where The choice is clear. We have to do it with shells because we really don't know how to do it with washers.